Hello, so in this video I'm going to be talking about what to do if after you run your experiment you find that your data doesn't form a nice linear relationship. How you can manipulate that data into making that linear relationship, which you can then use to build an equation. This process is going to be called linearizing the data. Go figure. So right here I have a box that many science classrooms have. So this is 22.4 liters of gas that is currently at standard pressure and thankfully slightly warmer than standard temperature. So we're going to be looking at what would happen if you were to sit on this box. Well, you are going to be then decreasing the volume of that box and increasing the pressure inside that box, and in the process making a chemistry teacher quite angry. Temperature is going to be held constant in this experiment just because we're going to assume that all the temperature is going to equalize with the rest of the room. So with that, let's actually then look at the data that you might get if you were to run this experiment, assuming that the chemistry teacher doesn't kill you first. So I have now completed this hypothetical experiment. Don't worry, no boxes were really crunched, so no chemistry teachers are currently trying to kill me. So let's take a look at what we've got. First thing I want you to notice is that up here at the top, I labeled both of my columns. A lot of times students just want to dive in and start putting their data on row number 1. That's what I used to like to do. But it's important to resist that temptation. Put that title in first. Put that label in for that column first. Otherwise, as this gets bigger and bigger and more complicated, you're going to end up confusing yourself. And almost more importantly, you are not the only one that is going to be using this table. Your lab mates will be, and if you have any questions, you might be calling your teacher over for help, and if you don't have these labeled, your teacher is going to have a very difficult time orienting themselves in order to figure out what's going on and answering your questions. So let's take a look. We got volume over here on the left, measured in liters, and we got pressure measured in atmospheres, and that's pretty much all that I can tell. I mean, I can look at this table and go, hey, look, as volume goes down, pressure goes up. But that's almost the limit as to what a table can really show. In order to understand more about what's going on, we really need a graph. So in order to make this into a graph, I'm going to again select those first two columns, go to Insert, go to Scatter Plot, and again, I just want this basic scatter plot. I don't want it doing anything overly fancy yet. So scatter plot. Ooh! This is not a linear relationship. Well, you probably could guess that given the title of this video, but yeah, this is definitely not showing a linear relationship. And I could go up to this quick layout and click on that in order to give me a line of best fit, but you can see that this line of best fit isn't fitting anything. It's just thrown on the top. The computer took my command of, hey, look, make something, and it made something the best that it could, but it doesn't fit anything. And we can take a look at this equation box and go, yeah, this really doesn't tell me anything. It's just the mathematical fit of this, which doesn't, again, fit. And in the previous video, I talked about this r squared, that root mean squared. 1 is perfectly matched. 0 is perfectly unmatched. And the lower that number gets, the less of a good match that it is. And you can see that here, when we've got something at 0.4, it's obviously not a good match. For most of the stuff in physics, we're going to be in that high 0.9 something, so 0.95 or better is usually what we end up seeing, but this is going to be a judgment call. That root mean squared is just a tool to figure out, is this a good fit? And looking at this, we know that it's not. So we can go ahead and just delete this graph because it's not showing us anything that we need. But before that, we need to take a look and go, hey, look, this is an inverse relationship. And in order to linearize, in order to make a straight line out of this, because it's an inverse relationship, we need to take the reciprocal of either volume or pressure. It doesn't really matter which one we choose. In this case, I'm going to choose to take the reciprocal of volume. That way I'm going to end up with an equation that it's pressure equals whatever. So we can go ahead and select this. I can hit the delete button, and it's now gone. So in order to then make that linearized graph, I'm going to go and insert another column. So I'm going to select the B column, and I am going to right click, and I am going to go insert. And that inserted a line of cells down here. So I'm going to be taking the reciprocal of the volume, so I'm going to first thing label my column. And specifically, I'm going to label this 1 over volume. And the unit for this is going to be 1 over liters. Now, you notice that this title was a little bit too big for the column width. I can again resize the column either by going over this line and moving left or right, or I can also double click and that automatically resizes it. So I could then grab a calculator and do 1 over 22.4, enter 1 over, and put all those numbers in. But that seems a lot of work. I've got 16 numbers here that I would have to do that and manually enter and hope that I don't have any typos. A much easier way of doing this is to use the formulas in Excel. So in order to do that, in order to tell Excel, hey, look, I want to use a formula, the first thing I'm going to do is hit enter. And that's going to then say, hey, look, this is a formula. I want you to do math. I want the readout to equal everything that I'm going to put in next. So I then want it to do that math, taking the reciprocal, so it's 1 divided by the cell over to the left. So what I'm going to do is I'm going to click on that cell. So 1 divided by A2, that's going to be the value of the cell in A2, is going to equal something that's pretty close to 0, because 1 divided by 22 is going to be small. In order to then change the formatting on this so it doesn't look like 0, what you can do is up here by number, you can add numbers of 0. So let's go with 3 significant digits for the moment. So now we've got our 3 significant digits, so it's not actually looking like 0. Now we could do this again. We could do equals 1 divided by A3. But that's going to get rather tedious, especially since I then need to do this for that as well. The other thing that you could do is, you see how on this box that's surrounding that now 0.0499, you see that small square in the corner? I could grab a hold of that, and you can see how my my cursor changes. I could grab a hold of that and pull it down. And by pulling it down, what that is going to do is copy that all the way down. So if I click on this, it basically did all of those things for me. It applied that same formula all the way down. So it's taking 1 divided by the cell over to the left and doing that calculation. So now I have all of my, I've now taken the reciprocal of all of my volumes. So now let's see whether we've actually succeeded in our goal of linearizing this relationship. So I'm going to grab both of these right here, and I'm going to go insert and scatter, and just the plain scatter, and see whether it's now a straight line. Oh, that looks like a gorgeous straight line. This is wonderful indeed. So what am I going to do with this? Well, we're still missing a lot of things that are necessary in this graph. So again, I'm going to go up to the quick layout. I'm going to go to this layout number 9, just like last time. I'm going to get rid of the key, because the legend, because I really don't care that much about it. And now I'm going to then call this graph compressing the chemistry teacher's cube. All right. And now we can go and label our axes so we don't confuse ourselves. So over on the left-hand side, that's going to be the pressure. And the pressure was measured in atmospheres. And then on the bottom, that is not volume. Remember, we took the reciprocal of the volume. So this is going to be 1 over the volume. And the units for that is going to be 1 divided by liters. So now I've got a graph. And I also have this equation sitting right here. Let's move that to right there. All right, so you can see that here we've got a really good r-squared function, r-squared value. It is equal to 1. Probably because I made sure that the numbers were going to work out like this ahead of time. So we are now looking really, really good. So now let's take a look and make this equation fit our data. So it's not going to be y and x, it's going to be pressure and volume. So our y values, that's again going to be pressure. So, and then we have to put in our units. So, our units for this is going to be units of rise. So, that's going to be atmospheres over our units of run. So, our units of run is 1 over liters. So, if we do that, it would be 1 divided by 1 divided by liters. Or we could also then just say, hey, look, that's just multiplying this by liters. So my unit is going to be atmospheres times liters. And then my x value, that one's going to be 1 over the volume. So, do the units work? If my x value is 1 over liters, that's going to cancel the liters. That's going to give me atmospheres. And that's what we want for pressure. So the units all work out. Now, we're now looking over at the far right-hand side. That's where the y-intercept is. And I can look at this and go, hey, this 0.001 atmospheres is really, really small. That is just about going to round to 0. And in physics, a lot of times what we're going to end up with is something y-intercept that's really close to 0. It's really close to being a direct relationship. And you're never going to be wrong by keeping your y-intercept. But if your y-intercept is about, call it less than 5% of your median values. So that would be like here-ish. So your middle point, this is very, very small compared to that. So we can actually get away with just going through and deleting this because it really doesn't have any effect on the outcome of this equation. It rounds to 0 is another way of looking at it. So there we have our equation. We can also get rid of that r-squared since we've now looked at it and go, yeah, that looks good. And so we now have an equation that explains how pressure is affected by that volume. And if we were to plug in a given volume, we could then make a really good guess as to what the pressure inside that box would be. This is going to be a very key skill throughout the year, because this is going to allow us to run an experiment, generate an equation, and then use that equation in order to then make predictions about how the world works. So now let's take a look at this relationship between time and distance, specifically how far an object has gone over a certain length of time. So let's go ahead and take a look at this graph, because the table just tells me, hey, look, they're both going up. So insert, we're going for our scatter plot, And now I can see that we have something that looks sort of like it might be a linear relationship. I'm not 100% sure because the data is noisier, which means that it's jumping around a little bit, but we can go ahead and apply this quick layout to it and see what we see. Let's actually make this a little bit bigger. So, up here at the beginning, it's above the line. Throughout all this middle, it's pretty much below the line. And then at the end, it's back to being above the line. Now that I've applied this line to it, I'm not 100% sure that this is really and truly a linear relationship. It could be parabolic. It could be looking like this. So let's go ahead and test that. So in order to linearize a relationship like this, we can take the axis that isn't quite pulling its weight. So the y-axis might be growing faster than the x-axis. So we can then try this. We can do what's called a test plot. So let's go ahead and click over here and go Insert. Now you can see that even though I inserted more cells, Excel's smart enough to go, hey look, we're going to have our data be these two columns. So let's put another column in here, and we're going to be squaring our x values. So we're going to have time squared, and that's good, of course, going to be then in seconds squared. And I'm going to put in another equal sign to tell Excel that I want to put in a formula, and I'm going to select this and I'm going to square it. So I'm now going to bring this down, and now I'm going to plot the time squared versus the distance and see what that then gives me. So I'm going to insert a graph. That looks linear, and we can, I ended up inserting it twice. There we go. And so this looks perhaps a little bit better, but let's check and see. So let's go. Let's see, we need to be in chart design, we want quick layout, we want option 9. And so yeah, this looks better. And now we can compare our R values as well. So that root mean squared, that R squared. So here we're 0.994, so really, really close to 1. And even 0.96, that's okay, but not nearly as good as this fit here. So I would say that what we actually have here is a parabolic relationship. Now this is one of those things where figuring out exactly what you're going to be looking at and what fit's going to work better is something that you don't really know until you check. So this is going to be one of those where the more data that you have, the better you're going to be, because you're going to have more information. And the bigger the range of data that you have, the better. And that's going to be well shown in this next example that I have for you. So I've already made this graph using what would possibly be a good amount of data. So I have 11 data points on this graph. It looks linear. But a lot of times in physics, just having 11 data points, or just even having 100 data points, isn't going to get you as much information as you really need. You also need to have a good range of data points. And the rule of thumb for that is to have at least like a factor of 5. So if my lowest data point is 5, then my highest data point should be about 25. It's that factor of 5. So if I expand the amount that my graph is showing, that's starting to look like it might be a little bit curved. I don't know, but I've going from 5 to 20, so I'm better. It might be not straight, I'm not sure, but if I am able to take more data over a bigger range. Now I can definitely see what we're dealing with isn't a linear relationship, but a sideways opening parabola. So this is definitely not linear. To linearize something like this, what you're going to do is, again, square the axis that isn't quite keeping up. And so in that case, it's the y-axis that's not keeping up. So we're going to square velocity. So I'm going to put in another column here that's going to be for velocity squared. And that's going to be in meters squared per second squared. And this should be in meters. And this should be in meters per second. So now let's take a look at how we can do this. So we can ask again for a formula. We're going to take this value here and we're going to put in a caret for squared and hit equals. And now I'm going to take this and bring it all the way down. So now I'm going to select my A column and my C column and go insert chart. And now that definitely looks like this beautiful straight line linear relationship. So in order to do that with that sideways opening parabola, I needed to square velocity. From here, I can go in, label my axes, and so forth. This is one of those things that is a difficult concept the first time you see it. But it's one of those tools that is going to be very powerful for us as we go throughout our year. It's going to be one of those things that you're going to get lots and lots of practice on it. So if this is something that's still confusing you right now, don't worry, we'll get there together. With that, I wish you the very best of days.